but also to have a good time.
Welcome to the Standard Deviant's Video Course Review Series. If you've gotten this far, you've already removed your videotape from its video sleeve and safely placed it into a compatible video cassette playback machine like this one here.
On the video machine's control panel, notice the various buttons and switches that allow you to adjust the pace of this video presentation. You can pause the tape, stop the tape, or rewind the tape if you get interrupted, confused, or just enjoy watching complicated mathematics presentations over and over again.
We've also included some informative insert cards in your video sleeve, which contain a complete outline of our presentation, as well as other important facts and figures that will help you follow along.
Along those same lines, while videotape viewing is a 99.9% safe activity, in the unfortunate event of an emergency water landing, this videotape can also be used as a flotation device.
One last warning. To ensure your best opportunity to receive a passing grade in class, you must attend the lectures, do the homework, and study really, really hard. This videotape is only intended to be a supplement to your classroom experience.
Thanks for your time and attention. We hope your learning experience is a safe and pleasant one. From all of us here at the Standard Deviant headquarters, have a great trip.
To understand the material covered in this videotape, you'll need to have a solid understanding of the stuff you learned in calculus, especially your advanced integration techniques. We'll cover some review topics as we move along, but we expect that you know the power, product, and quotient rules for derivatives, tons and tons of integration rules, as well as the calculus of the exponential, logarithmic, and trigonometric functions needed to solve basic problems.
Part 1. Introduction to Differential Equations.
Section A. What's a differential equation?
Good question, one that deserves a good answer. The short answer is that a differential equation is an equation that has a derivative in it. Well, that's about as helpful as defining mathematics as a subject with a lot of math in it. To really understand what a differential equation is, we need to look back at some other types of equations from algebra that we're familiar with.
First, linear equations, such as 2x plus 5y equals 15.
Next, quadratic equations, such as 3x squared plus 5x plus 7 equals 0.
Next, radical equations, such as the square root of the quantity 5x squared plus 4x, all minus 3, equals 0.
And finally, the equation for trouble, which you see here.
All of these equations, except for that last one, are algebraic equations. They have unknowns in them, such as the variables x and y, and they all need different techniques to solve them. We won't go into those techniques here because, in theory at least, if you're watching this tape, you already know that stuff.
A differential equation, on the other hand, is not merely an algebraic equation with unknown variables. It's much, much more. A differential equation is an equation with some derivatives of an unknown in it. Hence our original definition. A differential equation is an equation with a derivative in it.
So what's the big deal? Why study this stuff? Well, differential equations are crucial to many scientific and technical professions. Differential equations are used to represent rates of change or time-varying phenomena, such as electric currents in electrical engineering, compounding interest in economics, and rates of chemical reactions in chemistry.
Here's an example of a differential equation. Y prime minus y equals 0. In this case, the y prime is the derivative of y. To solve this equation, we would need to find a function, y, such that its derivative minus itself equals 0. We'll show you how to solve an equation like this in a minute. But first, let's talk about form.
Differential equations can be written in three different forms: the derivative form, the differential form, and the differential operator form. Let's take the differential equation y double prime plus y prime equals 0 and talk about form.
In the derivative form, our equation would look like this, with the prime notation. See those little primey things? Those are primes, and that means we're looking at the derivative form. In the differential form, it would look like this, with the dy dx notation. It's read the second derivative of y with respect to x plus the first derivative of y with respect to x equals 0. The dy dx thingies tell you that you're looking at the differential form. So primey thingies, derivative form. dy dx thingies, differential form. Got it?
The third form, the differential operator form, looks like this, with capital D's representing the derivative. This is read, the second derivative of y plus the first derivative of y equals 0. Here, D is called a differential operator. We won't use this notation in the tape, but you should be aware of it in case your professor springs it on you in class.
Actually, you should be able to recognize differential equations in all forms, but mostly we'll be working with the first two because they enable us to manipulate the equations a little more. And that's what we like to do most, manipulate equations.
If we look closer at the differential form of this differential equation, we can see that x is the independent variable and y is the dependent variable. This is because we are taking the derivative of y with respect to x. The independent variable is always the variable that is on the bottom in differential form, and the dependent variable is the one on top.
Differential equations can be categorized as either ordinary differential equations, ODE, or partial differential equations, PDE. The difference is in the number of independent variables that an equation has.
Ordinary differential equations contain derivative terms of one or more dependent variables with respect to only one independent variable. Now, let's decipher what I just said. Remember that the independent variable is the variable a derivative is taken with respect to, or, in other words, the one that is on the bottom in differential form.
An example of an ordinary differential equation is y double prime plus y prime plus y equals 0. This is written in the derivative form. See those primey things? Translating this into differential form, we get the second derivative of y with respect to x plus dy dx plus y equals 0. As you can see, all the derivatives in this equation are taken with respect to x, and the last term y is not a derivative. So x is the only independent variable, making this an ODE.
Once again, partial differential equations contain partial derivatives, which are derivatives taken with respect to more than one independent variable.
An example of a partial differential equation is this sucker. The second partial of u with respect to x plus the second partial of u with respect to y equals 0. Here, u is the dependent variable because it's on top, but notice that there are two different variables on the bottom, both x and y. That means that we have two independent variables here. Oh, and don't be fazed by those little curly D looking things. They just represent the partial derivative.
Now that you can tell the difference between ordinary and partial differential equations, just know that in this tape we will focus solely on ordinary differential equations. Partial differential equations are a whole other ballgame, and your school probably has a whole course devoted just to them. If you're confused about any of the definitions we just covered, go ahead and rewind the tape and watch this section over again. Otherwise, we're just going to plow ahead.
Section B, types of differential equations.
There are two types of ordinary differential equations that you need to be able to recognize. There are linear differential equations and nonlinear differential equations.